Welcome to the course on Python for data analytics, machine learning, and generative AI. In this session, we will focus on statistics, which forms the backbone of data science and machine learning. By the end of this session, you should be comfortable applying statistical concepts using Python and interpreting results correctly. In this session, we will learn how Python helps us summarize and understand data using statistical measures such as mean, median, mode, variance, and standard deviation. These concepts form the foundation of data analysis, research, and machine learning. Let's begin by understanding why descriptive statistics matter in data science. So let's open Jupyter Notebook, write some Python code together, and bring the concept of statistics to life. First, we use Python statistics module. Import statistics as stats. Statistics statement in Python brings in the built-in module for calculating mathematical statistics of numeric data. It provides functions for calculating mean, median, mode, standard deviation, and variance. When we import it, Python gives us ready-made tools, so we do not need to write complex formulas. Next, we create a data set. Think of this list as a real-world data, such as test scores or daily sales numbers. Measures of central tendency include mean, median, mode. Each of this gives a different perspective on the same data. Choosing the right measure depends on the nature of the data set. The mean is simply the average. Python adds all the values and divides the total by how many numbers are present. This gives us a single value that represents the center of the data. The mean of function from Python's statistic module is used to calculate the average of a set of numeric values. The median of gives the middle value. Python first sorts the data and then picks the value that lies exactly in the center. If the data set has an even number of values, Python takes the average of the two middle numbers. The mode of tells us which value appears most frequently. In our data, one number repeats more times than the others. So, Python identifies it as the mode. This is useful when we want to know what value is most common. Measures of dispersion quantify the spread, variability, or scatter of data points around a center value, mean or median. Key measures include range, interquartile range, variance, and standard deviation. Variance shows how spread out the data is. If values are close together, variance is small. If they are far apart, variance increases. Standard deviation is the square root of variance. It is easier to understand and commonly used in research and data analysis. The interquartile range, IQR, is a measure of statistical dispersion that represents the spread of the middle 50% of the data set, calculated as the difference between the third quartile and the first quartile. It is given as IQR is equal to Q3 minus Q1, making it a robust measure less affected by extreme outliers than the total range. Finally, we print the results so we can see all values clearly. Sometimes data does not have just one mode. In this example, two numbers repeat the same number of times. Instead of choosing one, Python returns all modes. This is important when working with real data sets where patterns are not always simple. Now we move to NumPy, which is widely used in data science, analytics, and machine learning. NumPy is faster and more efficient, especially when working with large data sets. Here, we store the same data inside a NumPy array. NumPy calculates mean and median using simple function calls. The syntax is clean and the results are reliable. When calculating variance and standard deviation, we specify that the data is a sample and not a full population. This is common practice in academic research and statistical analysis. NumPy does not directly calculate the mode. For that, we use another library called SciPy. SciPy works together with NumPy and provides advanced statistical functions. Using SciPy, Python identifies the most frequent value in the dataset. The line from SciPy import stats gives us access to statistical tools, while from SciPy.stats import IQR specifically imports the function used to compute the interquartile range. Let's now see how to manually calculate the concepts. Now let us calculate everything manually. This part is important because it helps us understand what Python is actually doing behind the scenes. We add all the values and divide by the number of items. This is the same formula you learned in basic mathematics for manually calculating mean. For manually calculating median, first we sort the data. If the count is odd, we take the middle value. If it is even, we average the two middle values. To calculate manually mode, Python checks which value appears the most by counting each item. To manually calculate variance and standard deviation, we subtract the mean from each value, square the result, and add everything together. Then we divide by 1 less than the total number of values. Taking the square root gives us the standard deviation. Skewness tells us whether the data is distributed evenly or if it leans more towards one side. When skewness is approximately 0, the distribution is symmetrical, which means the left and right sides mirror each other. If skewness is greater than 0, the distribution is right skewed, also called positively skewed. This means the tails extends towards higher values. If skewness is less than 0, the distribution is left skewed or negatively skewed, where the tail extends towards the lower values. Kurtosis describes how heavy or light the tails of a distribution are compared to a normal distribution. When kurtosis is around 0, the distribution is normal, also called mesokurtic. If kurtosis is greater than 0, the distribution has heavier tails, known as leptokurtic, which means more extreme values or outliers. If kurtosis is less than 0, the distribution has lighter tails called platykurtic, which indicates fewer extreme values. Next, the code demonstrates two ways to compute these measures. First, using SciPy, which is one of the most common approach. We import skew and kurtosis from SciPy.stats, calculate the value for the dataset, and print the results. By default, SciPy returns excess kurtosis, meaning it compares the distribution directly to a normal distribution baseline of 0. Second, using pandas, which is ideal when working with datasets. We convert the data into a panda series and use the built-in skew and kurt methods to compute the same statistics easily. Finally, script visualizes skewness using histogram. 3 datasets are created. One symmetric, one right skewed, and one left skewed. For each dataset, Python calculates skewness and displays a histogram so we can visually connect the numerical values with the distribution's shape. So skewness helps us understand direction of asymmetry, while kurtosis tells us about tail heaviness and outliers. Together, they provide a deeper understanding of how data behaves beyond simple averages and spread. Let us summarize. In this session, you learned how to calculate statistics using basic Python, how to handle multiple modes, why NumPy, SciPy are performed in data science, and how to calculate statistics manually for deeper understanding.
Skewness and kurtosis for direction of asymmetry and tail heaviness.
Thank you.